So during the session, I want to talk about the unique environment of embedded machine learning. I want to talk about some of the unique challenges that you have when building artificial intelligence and machine learning applications for embedded environments. I'm going to talk about how your software or our software needs to make the most of the hardware that's actually present on those embedded systems, because it can be more limited. We'll talk specifically about some of the work that we've been doing with Tensorflow to enable that to run on some different systems. I want to talk about open standards and how that can help us to reach our goals with machine learning applications on embedded systems. Okay, so just to tell you a bit about CodePlay. So as was said, we're based in Edinburgh in Scotland, which is not too far away from here. So we're a specialized software company, and we've had many years of developing compilers, runtimes, debuggers, so quite a lot of low-level tools that developers use in their everyday. We've delivered many standards-compliant systems for some of the largest semiconductors. So you can see some of them in the corner of the slide there. We're also heavily involved with a lot of open standards. So we chair the SYCL open standard. We also have people on the Vulkan standards and OpenCL as well. And I'll talk a little bit about some of those standards later on. So the company actually has a background in games development. Our founder developed games, and then he went on to found the company, and he started developing compilers for things like the PlayStation. And that then transitioned into mobile, which is why you can see Broadcom and people like that on there. And now, in the last, I suppose, year or two, as machine learning as a kind of industry realized that GPUs and other accelerated processors were perfect for this sort of algebra and the sort of operations that they were doing, it's kind of been a natural move into that space. And that's how I came to talk today. So these are some of the sorts of machine learning applications that you might see. These are quite randomly chosen by me. But you've got things like Siri, where you can obviously ask it a question, tell it to do something, and hopefully it will give you a good response, or it will do the right thing for you. You've got things like financial applications, so machine learning and artificial intelligence applications that are trying to read markets. They're trying to predict future movements in markets. They're doing day trading and stuff like that. And you've also got things like medical applications. I've heard people talking about that during the conference, basically getting a machine to look at a load of scans and images to try and detect diseases and things like that. And the other one is a typical enterprise application where you have a device that can scan an object, in this case like a parcel, and it will probably tell you how long it takes to get to Mexico or how much it costs to post it and stuff like that. But all these applications have some things in common. So the things that they have in common is that they're quite limited in the kind of location that they can be used. And they rely quite heavily on cloud infrastructure usually. So they have big banks of servers sitting there with loads of GPUs in them, and they can crunch out the predictions and the operations that they need really quite quickly. They also have access to a fairly unlimited amount of power. I know mobile phones maybe necessarily don't, but generally a lot of these fixed applications will be plugged into a wall socket, so they don't need to worry about how much power that they're consuming. So I've heard a few people talk about autonomous cars at the conference, but this is the reality of like a proper kind of embedded system. You can't have a car relying on connectivity to make decisions about what it's going to do, like on an immediate basis. The lag is too much. It needs to make decisions like split seconds or split microsecond decisions. So it can't rely on connectivity. I saw a picture of the the British company, I forget the name of them, that are doing the autonomous car. In the boot or the trunk of their car, they had a huge number of power supplies that were powering the GPUs and everything that they had in their car. I certainly wouldn't envisage that as being a realistic architecture for an autonomous car. You can't have a car that just has a load of power supplies in the boot and needs to be recharged all the time. So we need to be able to use more limited processors that are taking less power. And the last one, which is obvious one to lead on to, is that they're power constrained, so they need to make the most of the power that they have. Okay. So this then provides quite a unique challenge, particularly in this example of an autonomous vehicle or a semi-autonomous vehicle. You can see all the data sources that are coming into this car. The gray ones are just normal cameras, and I understand that you could have probably like over 20, 40, however many. They seem to be planning on having a crazy number of cameras on cars. They also have things like Lidar detection. So if you don't know what Lidar is, it's basically a thing that sits on the car, and it sends laser beams all around it. And from the reflection of those laser beams, a bit like radar, it can then build a picture up of the environment that's surrounding the car. I've seen examples of this. I possibly should have put one up, but it's quite amazing what they can do with that. And then you have normal radar, which is used at the moment for things like object detection behind the car when you're reversing and stuff like that. But the point I'm trying to make is that with all this data that's coming into the car, it's all very well and good. You could say, right, I can write a machine learning application that, using all these data sources, can make really good decisions about when it's driving itself. But all that needs to be processed, and it's an extremely complex thing to do. Okay, so a lot of people have talked about just using cameras on cars, and this has exposed like a few problems where this is a very good example, where the machine learning application sees 2 cars, but it also sees 3 bicycles and a person, because the bicycles and the person are on a photograph on the back of the car. So this kind of reinforces the fact that you can't rely on one data source to make decisions about when you're driving. So that's why all those different sensors have been put onto that car that I showed you in the last slide. Okay, so this is a slide that I got from our CEO, but he likes to show this because, I guess, because of the business that we're in and the advantages that we can give people. But this was something that Google said last year about how much processing power that they need in order to build like a fully autonomous vehicle, which is 50 teraflops of performance, which seems like quite a lot to me. I'm not a hardware expert. But the point of this is that point up there is really quite far away from where we are today. And it's just not realistic that hardware is going to catch up to the degree that it's needed in order to achieve that sort of performance. You can tell that's not my slide, it's got transitions. Okay, so the conclusion that we've come to is that it's the software that's going to drive us towards that target. It seems to be the only way that that's likely to happen. And this is a picture from one of our partners that we work with, Renesas, but it's trying to show all the different things that a developer needs in order to build like a machine learning or any sort of application for some sort of vehicle, whether that be autonomous or not. So the bit that we're involved with is the bit that's highlighted there. So this is basically the parallel capabilities of the processor being exposed to you as developers. So the idea is that that we can provide a layer that makes it easy to program against their accelerator processor that they've designed specifically for this purpose. Okay, so question then is, how can software get us there? So in the last few years, obviously with particularly TensorFlow, which is the big buzzword or buzz product of the moment, but it's quite obvious that in the last few years that deep neural networks and the work, the advancements that have been made in that field are what's actually going to make machine learning applications for the sorts of things that we're talking about possible. And this is accelerating the development. So you've seen the progress that Waymo have made. You've seen the progress that all these companies are making. But again, we go back to this challenge of how do we make the most effective use of the processors that are actually inside the vehicle. So I said before, I'm not a machine learning expert. I'm also not a maths expert either. But I wanted to give you a bit of a background on like what's actually happening under the hood when you're using something like TensorFlow, a machine learning framework. So you can see TensorFlow is partially named after tensors, which are these n-dimensional matrices which can be represented by arrays. So you've probably seen it in other talks where they have these huge matrices that contain the data that you want to feed into your neural network. So the kinds of operations that are done on those matrices are done using something called linear algebra. And these types of operations, as you can see, they're quite complex, but that also means that they're quite processor intensive as well. So TensorFlow relies very heavily on these linear algebra operations for doing its processing. And this involves many, many matrix calculations. And as I said, matrix calculations are processor intensive. You could have, thousands by thousands matrices that need to be multiplied together and pass through multiple operations. Okay, so I wanted to give you kind of a bit of an idea of how this translates, like from TensorFlow or a machine learning framework onto the actual hardware. So this is where, when I talk about parallel hardware, this is where we can make significant improvements to the performance of applications that are running with TensorFlow by using parallel hardware. So this is obviously CPU and a GPU. A CPU has a small number of cores. A GPU can have thousands of cores. The main difference is that a CPU can carry out different types of operations on multiple cores, whereas a GPU tends to only be able to do the same operation but across lots and lots of cores. Yeah. So from a practical point of view, what that means is that if you've got two large matrices, and you're using this on a CPU, you can only pass in this case, 4 operations at one time in order to process the whole lot. To run serially, these operations are obviously quite limited in the sort of bandwidth that you can put them through. So then the difference when you're running on a GPU is that you can have these 2 very large matrices. I obviously didn't bother filling in the whole thing, but you could basically do an operation on those 2 matrices pretty much in one operation, because the GPU might have thousands of cores that are available to it. So what does this mean for something like TensorFlow? So I found this chart from a project that someone was working on, and it basically shows you the sort of effects that using a GPU versus a CPU can have on the performance of your application. So as I said, since linear algebra involves lots of similar calculations, they can be run totally in parallel on the GPU, whereas on the CPU, you can see that the performance deteriorates the larger that the matrix becomes. Whereas on the GPU, the larger the matrix becomes, almost the better the performance that it manages to achieve. So just to give you an idea of how TensorFlow performs all of these operations, it uses a library called Eigen that has a nice owl as its mascot. Eigen's a C++ library, and it already has implemented a lot of parallel execution of a number of operations that are linear algebra that are needed basically by TensorFlow to run all of the operations that it provides. So it offers the benefit of running things in parallel, but it also offers additional performance benefits that I'll go into. So the Eigen library uses something called kernel fusion. And what this involves is basically, as it would describe, fusing different operations together so that it can be run simultaneously or in parallel on the processor. So one of the other things to bear in mind is that it's not just the execution of the calculations that costs time and processing effort. There's also the effort of putting things in and out of things in and off the processor as well. So this is memory movement. The memory movement can often be slower than the actual calculation that's performed on the cores. So just to give you an explanation of what a kernel is, if you don't have a background in parallel programming. So a kernel is effectively just a function that you can define that you give to programming framework that allows you to do parallel programming and allows you to apply that on some data. So the simple example here, this is using Sickle. So this is defining a really simple kernel that just does C equals A plus B. So it's not doing anything massively complicated. The key bit here is that the parallel for part is basically saying here's a big data set, run this operation in parallel on the hardware that's available to you. So you don't need to worry about what the hardware is. The language will then translate that into so that it can be done. So what that means in the example of Eigen is that these two operations, so B times C and then addition to D, can actually be combined together so that there's no expensive memory movement between the GPU and the host, as we call it, which is off the GPU. Okay, so to give you an idea of the sort of performance improvement that you can see by using some of these techniques, I thought I'd put up some charts that give you, that will give you an idea of how much that is. So you can see that, perhaps if I explain this for better context, so there's effectively 3 different kernels that exist. So this might be, as I say, an B times C, and then an addition to that, and then a further operation, might be multiplication or something like that. But this shows the sort of performance increases that you can get by fusing those three operations together. So you can see that it's gone from taking it's gone to taking almost like a third of the time that you would expect the three kernels to take if they were run independently. You can also see the small chart in the corner there, which is showing like specific operations that TensorFlow uses, like convolutions and stuff like that, and the sort of increases in performance that you can get at a particular size of network there. Okay, so what does this mean for embedded applications, you're perhaps wondering? So as I've explained, embedded hardware is going to be a lot less powerful than the sort of thing that you're going to find in a data center in the clouds, where you can basically give it really quite complex operations to do, and it'll power through them, and that way your latency is really how long it takes for the data to get there and back. But it really it means that running in parallel gives better performance out of the hardware that we have, but it also makes the execution far more efficient, so reducing the amount of power that you can use. So as I said, in an embedded environment, you want to use as little power as you can, ideally, and you also want to make the most out of the hardware that is available. Okay, so I started to talk a bit about open standards and the ones that we're involved with. So NVIDIA has an ecosystem called CUDA, which enables NVIDIA hardware, including the GPUs that they manufacture. So SYCL is quite a similar sort of environment to CUDA, but it provides support for OpenCL devices. So what we're trying to do is, by supporting open standards, we can make sure that hardware has a standardized environment for developers to develop against. And we want to make sure that these are open standards and not some proprietary closed thing. So OpenCL, if you've not heard of it, so that is basically a cross-platform programming interface that allows developers to program with parallel applications for a range of different processors. It allows developers to use C for that purpose, and we have our own implementation of OpenCL, which we call Compute IORTA. So SYCL, which is another open standard, which is basically a higher level abstraction of OpenCL. So that supports modern C++, so it means that you can develop with standard C++. You can use templates. You can do all the things that you would expect to be able to do with C++. So we've actually used Compute CPP, our implementation of SYCL, to enable TensorFlow with a bunch of different OpenCL devices. So rather than having to use a CUDA GPU, you can use an OpenCL-supported device, which could be a GPU, or it could be a FPGA or something different. There are also alternative implementations of the standard too. Okay, so using open standards with TensorFlow, so these are what the current stacks look like. SYCL has been chosen as a way to integrate TensorFlow with OpenCL devices. There are a few different reasons for that. Eigen's a C++ library, so SYCL supports standard C++, so it makes the integration easier. Eigen uses C++ templates. Again, the ability to use templates makes things much easier as well. But you can see from kind of top to bottom where we have TensorFlow sitting on the top, and then we have the Eigen library that sits underneath and does all the heavy lifting, the linear algebra operations. And then we have these, I guess, CUDA and SYCL interfaces that enables Eigen to use the parallel hardware, the GPUs and stuff like that. And then we have these kind of, what's the words? Kind of translation interfaces where the instructions that are output by SYCL or by CUDA are basically these two formats, and it's these formats that the hardware underneath is able to interpret and is able to run the code that it's been given. Okay, so the benefits of the SYCL integration that's been done. So it means that you're able to target a lot of existing devices that are there, even already in the market. So there's hardware like Intel GPUs, there's hardware like AMD GPUs. There's also some work that we've been doing with Renesas to support their hardware as well, which is OpenCL supported. It basically means that you have a wider range of access to hardware, particularly when you're looking at things in an embedded environment. NVIDIA GPUs may not be the right choice for that. One of the other benefits of the approach that we've had with SYCL is that TensorFlow includes a lot of operations, convolutions, and all sorts of things. There's a good chance that if you're building a specific model for your own application or something like that, then you need to add a brand new operation because the ones that exist do not fit the needs that you have for your model. So you can add that using C++ as an addition onto the SYCL integration that's there. So the other benefit that we have is that the interfaces are staying the same and they're standardized. Okay. So that goes on to like benefits for, I guess, some of you as developers. It means that, although I've explained in a fair bit of detail how the layers fit together and some of the kind of more mechanical aspects, what it means for you is that you can run your TensorFlow applications accelerated without actually thinking about what the hardware is underneath. So that means that you can target a much wider range of hardware. It means that you don't have to rely on necessarily NVIDIA GPUs for accelerating your machine learning programs, and that's got to be a good thing. So as I said, it also means that you get support for a wider range of embedded hardware processors. Okay, so to go beyond just TensorFlow, I wanted to talk about TensorFlow because it's something that we've been working on, but that's obviously only one framework, and a lot of people have emphasized that over the last couple of days, that there are a lot of other frameworks that you can use for machine learning, and some of them have been around for longer, and there are likely to be new ones that come in too. So something that we're trying to do as well with our work with SYCL Open Standard is by integrating that with other frameworks. So we're working to integrate with OpenCV, which some of you may or may not have heard of. It's a vision library, which has recently added a neural networks part to it as well with the latest release. And also we continue to use open standards, OpenCL, and SYCL to achieve these things. One of the other things that I wanted to talk about is if you're into kind of developing machine learning stuff, I guess from scratch rather than just using a framework, then you'll understand that one of the basic building blocks of a machine learning framework is having linear algebra library and operations. So one of the things that our company does quite a lot of is research projects. Quite often they're funded by either European Union or Innovate UK. And one of the projects that we've been working on is SYCL BLAST, which is a linear algebra library that you can use, but is written using SYCL, so it means that it supports OpenCL devices like natively. And this is quite interesting because assuming that TensorFlow isn't the only framework that developers decide that they want to use to build machine learning applications, it means that we've got the potential to enable lots of different frameworks in OpenCL using this fairly standard BLAS library, which is fairly well known. So this is the way that we see the stack from top to bottom. The nice thing about these layers is that you can obviously replace them with different implementations of these different standards. So you have all the higher level frameworks like your OpenCV and TensorFlow along the top, and then you have kind of different ways that they're enabled on the parallel hardware. So OpenCV already has an OpenCL implementation, which is quite handy. So that can be enabled on any hardware that already supports OpenCL instructions. And then the other frameworks are enabled via SYCL, which in our case is using Compute CPP and Compute IORTA. But as I say, you can choose the implementations that you slot into those layers. So one of the things I wanted to talk about, which is a little bit of a shameless plug of sorts. So we kind of announced our move into this embedded machine learning sort of environment last month with Renesas, who are a system-on-chip manufacturer. So they have a range of hardware that they're releasing over the coming years, which is basically a kit that you can use to build software and hardware systems for automotives. So we are actually enabling OpenCL on those devices using our Compute IORTA implementation, which subsequently means that you can run things like OpenCV on the hardware, and it'll be run on their CV engine processor, which is a GPU-like processor that accelerates performance of your application. One of the other things I wanted to mention as well is that it has a CV engine accelerator processor. It also has an ARM CPU. So by supporting OpenCL, we're actually enabling you to program either of those chips. And we're hoping to make available a free version of that compiler very soon. Okay, so just concluding the presentation, just to say that we obviously believe a lot in open standards, and we think that offers the best environment for developers, offers the best choice of hardware too, and it offers a better development environment for use as developers as well. And hopefully, and we're really hoping that it will help you to reach your target with building artificial intelligence applications for embedded systems. And that's it. Thank you.